Hello everyone, my name is Guoxing Chen and I'm from the Ohio State University. Today I'm going to present our paper, Racing in Hyperspace, Closing Hyperthreading Side Channels on SGX with Contrived Data Race. Wenhao Wang and I are co-first authors and listed alphabetically. And the other authors include Tianyu Chen, Sanchuan Chen, Professor Yingqian Zhang, Professor Xiaofeng Wang, Professor Chenhuan Lai, and Professor Dongdai Lin. Okay. Intel SGX is a hardware feature that provides sharded execution environment called enclave to software applications, and which provide confidentiality and integrity of the enclave program against the privileged attackers such as the operating system. However, today's SGX design has been found to still be vulnerable to side channel attacks. And typical side channels include caches and branch prediction units or BPUs. And the typical attack works as follows. The attacker first prepares the side channels and then run the enclave code to leave some traces. And later the enclave code will be switched out and the attacker can learn the traces and infer the sensitive data accordingly. However, when switching out the enclave event will be triggered, which is the asynchronous enclave exit or AEX. Hence, AEX detection-based mitigations have been proposed, such as TSGX and deja vu. However, side channels enabled or assisted by hyperthreading does not trigger AEX, so they can bypass these mitigations. So what's hyperthreading? Hyperthreading is Intel's proprietary implementation of simultaneous multithreading. It enables a physical core to execute two concurrent code streams and the two called hyperthread. And the two hyperthreads share the same execution resources, such as the caches, BPUs, and the translation local side buffers, or TLBs. This table summarizes the side channels enabled by hyperthreading, and the first three can only be exploited by with hyperthreading enabled, because the store buffers and the floating point units or FPU side channels can only be exploited by concurrent execution, and the AEX and the TLBs will be flushed upon AEX. The other vectors, the caches and BPUs, can be exploited with or without hyperthreading, but hyperthreading enables the attacker to steal information without frequently interrupting the enclave. Besides introducing these new side channels, hyperthreading could also assist existing side channel attacks. First, hyperthreading helps reduce AEX. One example is the sneaky page monitoring attack proposed by Wang et al. When assisted by hyperthreading, the attacker triggers no extra AEX and could bypass the AEX detection-based mitigations. The second is that hyperthreading could invalidate some defense techniques that use Intel's transactional synchronization extensions, or TSX, which is Intel's implementation of hardware transactional memory. But TSX does not prevent an attacker who share the same physical core. So here's our research goals. First is to close all these hyperthreading enabled or assisted side channels. Second is to also be able to detect AEX-based side channel attacks. However, defending against hyperthreading side channel attacks is very challenging. Simply disabling hyperthreading does not work because there's no effective way to verify it. Instructions such as CPU ID, RDT, SCP, and RDP ID are not currently supported in enclave. For remote attestation, currently it does not contain information about hyperthreading. So one viable solution is to create a shared thread from the enclave program and ask the OS to schedule it on the other hyperthread so that no other process could share the same physical core with the enclave program. However, it's very challenging to reliably verify the scheduling arrangement by the untrusted OS. So we need a reliable physical core collocation test. Here's the overview of our scheme. So for each thread to be, for each enclave thread to be protected, called protected thread, we create an auxiliary enclave thread called shared thread, and ask the OS to schedule them on the same physical core. A collocation test will be performed in the beginning to verify this scheduling arrangement, and the protected thread will then frequently check AEX, because whenever an enclave thread is switched out, AEX will occur. And whenever an AEX is detected, the collocation test needs to be run again. And if the test fails, the program will terminate. The key point here is the collocation test. And we proposed a novel collocation test using contrived data race. To see how contrived data race work, let's look at this example. So the two threads operate on the same shared variable v, and v is inside the enclave, so the untrusted OS could not tamper with it. The protect thread will repeatedly perform the following operations: write 0 to v, wait for 10 cycles, and read v. And the shadow thread will repeatedly write 1 to v. So there's a clear data race between the two threads because they write different values to the same shared variable. When they're collocated, they operate on the same L1 cache. So the protect thread will read 1, the value written by the shadow thread with high probability. In contrast, when they're not collocated, they operate on their own L1 cache and they rely on cache coherence protocol for synchronization. However, the latency is around 190 cycles, which is measured on a Skylake CPU, and it's much larger than the time for one loop. So the protect thread will read 1 with very low probability. However, but to better explain the difference of the data race probabilities, let's focus on two measurements. The first is the communication time, which is the time it takes for the value written by one thread to appear on the other thread's memory hierarchy. And the second is the execution time, which is the time between one read and its preceding write or one thread. So in our example, when they're collocated, the communication time is much smaller than the execution time. So when the protect thread read, it's very likely it will see the data written by the other thread immediately. So there will be a high data race probability. And when they're not collocated, we can see the communication time is much larger. So it's unlikely for the protected thread to see the value written by the shadow thread in time. Here's the basic idea of contrived data race, but to defend the real attacks, the design needs to be refined. So in the refined design, both threads will read and write on the same shared variable. And the goal here is that when they are collocated, both threads will observe data race with high probability. So let's see, both threads will operate like this, and the communication time is much smaller. So each thread will read the data written by the other thread with very high probability. And when they are not collocated, we can see that the design goal here is that at least one of them observes data race with low probability. And here we can see the communication time is much larger. So each thread will have a low probability to observe the data race from the data written by the other thread. So now we have a way to measure the data race probability, but how can we use it to produce the collocation test results? So here we propose to use hypothesis testing. So both threads will perform multiple data race tests and calculate the empirical data race probability. And when the empirical probability exceeds its theoretical value, we will accept the null hypothesis, which is that they are collocated. Otherwise, we will accept the alternative hypothesis, which is that they are not collocated. And these two formulas are used to calculate the threshold given a specific significance level alpha to reject the null hypothesis. And here's a concrete example. So when 256 data race tests are performed, the probability of observing less than 242 data race is around 1%. This is the code for the collocation test. Due to time limit, I will not go deeper here. It's also included in the paper. And the next question is, how can we prove that our scheme is secure? In fact, a large chunk of our paper focuses on the security analysis, but due to time limit, I will just give a high-level description of the analysis here. So first, let's look at the security requirements. There are two necessary conditions to pass the collocation test. The first is that communication time should be less than the execution time. We'll explain this already. And the second is that the execution time for both threads should be roughly the same. To see why, let's look at this example. Assume the shadow thread runs much faster. So when the protect thread finishes one loop, the shadow thread could finish multiple loops. And most of the loop could only observe the data written by itself, resulting in low data race probability and fail the test. In fact, these two conditions are drawn from our theoretical model. I will not explain the symbols in detail. Simply put, they relate to the communication time and execution time. Next, let's look at the thread model. The attacker placed these two threads on different physical cores and run attack code on the remaining hype threads and try to pass the collocation test. And the method that the attacker could use to affect the communication time and execution time include flashing cache, changing CPU frequency, and disabling caching, or some combination of them. So this is our security analysis. First, we have a theoretical model. Then we'll also conduct empirical measurements on latency of cache eviction, latency of cross-core communication, effects of CPU frequency changes, and effects of disabling caching. Combining these empirical measurements with our theoretical model, we performed a theoretical analysis in our paper and conclude that for all the attack scenario, we considered that it's impossible for the attacker to meet both requirements simultaneously to pass the test. Now let's look at the implementation. HyperRace is implemented by extending the LLVM framework. So for the original code will be first represented as the control flow graph. And each basic block will be instrumented using LLVM. And by default, there will be one AEX detection code at the beginning of each basic block. However, if the block is very large, one detection may not be enough. So we will insert an extra AEX detection called array Q instructions within that basic block. Here, Q is a parameter such that between two AEX detection, there will be at most Q instructions. And basically, smaller Q means that more frequent AEX detection and leaves a smaller attack window for the attacker. The shadow thread code is also generated, and whenever AEX is detected, the shadow thread code and the protected thread code will call into HyperRace library to run the collocation test. And we adopt the technique introduced by Grass et al. For the AEX detection through monitoring the state safe area, or SSA, of the enclave. Next is the performance. There are two types of performance overhead. So the first is the runtime overhead. If we use this red color to represent the time of executing these three types of codes, along the timeline, the code runs like this. So the runtime overhead consists of two parts. The first is the AEX detection, and the second is the collocation test. We evaluate these two overheads separately. And then is the memory overhead, which is represented as the increased code size. We evaluate the performance on Nbench, a lightweight benchmark application for CPU and memory performance testing. And the runtime overhead due to AEX detection is listed here, and the different values of Q are evaluated. Basically, a smaller Q means more frequent AEX detection and larger overhead. And particularly when Q equals to 5, the geometric mean of the runtime overhead due to AEX detection is around 101.8%. Next is the runtime overhead due to collocation test. We fixed the number of Q to 20, and we can see from the figure that the overhead is almost linear with regards to the frequency of AEX. And particularly when 1,000 AEX occurs per second, the geometric mean of the runtime overhead due to collocation test is around 16.6%. This is the memory overhead. Under different value of Q, the memory overhead ranges from 16.6% to 37.7%. So far, we've designed and implemented a novel collocation technique to close the hyper-threading side channels. The lesson we learned from this project is that hardware design is usually performance-oriented. But how about their security implications? What can we do if it is vulnerable? And we demonstrated in our this paper that a software approach could mitigate the threat. But in future, we believe that a composition of software solution and hardware feature might help strike a better balance between security and performance. For example, if Intel could temporarily shut down hyper-threading when the CPU runs the enclave code, the problem can be simplified. And that's all for my presentation. Thanks, and I'm ready to take questions.
All right, we have a few moments for questions. If you have a question, please approach one of the 3 microphones and state your name and affiliation. Okay. Just a quick correction. I had said this was the first time, but you've actually presented at Infocom some related work. Is that correct?
Yeah.
Okay. Let's see. If you have other questions, you're welcome to catch Guoxing later here, and you can talk to him about the Usenix paper or the Infocom papers. Anyone else for the mics? Last call. Okay, sorry, I can't see too well from all the spotlights. All right, well, let's thank the speaker again. Thanks again.
Thank you.